Welcome to homework.
So in this problem, we're going to have to use the concepts of binding energy, which is simply the energy of required to bind a nucleus together. The electromagnetic spectrum will come in handy, including energy of including energy, wavelength, and frequency concepts, and then we're going to use the concept of blackbody radiation. We use Wien's law, which states that the maximum, the peak wavelength of a blackbody is inversely proportional to the temperature. All right. So for part A, we're gonna find the binding energy, and that's equal to the difference in the rest masses times c squared. And so the difference in the rest masses, remember this is 2,1 hydrogen, otherwise known as deuterium. And so here you have, you're going to have the mass of the separate components, the mass of a neutron plus mass of a proton, minus the mass of the deuterium, that is delta M, that is the change in rest mass, times c squared. And so mass of neutron, we're given 1.008665, mass of hydrogen, proton 1.007825. I'm not going to write those down, but they're given in the problem. Basically, you take the sum of those, you get 2.01649 minus the mass of deuterium, which is 2.014102, and these are in units of U, atomic mass unit, times c squared. And so U is in SI units is 1.66 times 10 to the minus 27 kilograms, and C, of course, 3 times 10 to the 8 meters per second. You square that, and so put this all in, and you get a binding energy value that's very close to 3.0126 times 10 to the minus 10 joules. This is, when you do the conversion to electron volts, this is about 1.5 giga electron volts, so billions of electron volts, really high energy. Part B, gonna write with blue ink here. We know that energy is equal to hc over lambda, quantized energy, and so lambda, this lambda will be equal to hc over the binding energy we just calculated. H, Planck's constant, is 6.626 times 10 to the minus 34 in SI units, and C is 3 times 10 to the 8 meters per second again, and that's divided by this value of 3.0126 times 10 to the minus 10 in joules. If you keep it in joules, you don't have to worry about energy unit conversions, and you get wavelength in meters, which turns out to be 6.598 times 10 to the minus 16 meters. So this is obviously really, really, really low. And so which means that by Wien's law, so that's part B, part C, which I'm going to write in red ink, by Wien's law, you have lambda max, in this case it's the same as lambda, it's equal to B over T, and you turn it around, you get temperature as B over lambda. It's going to drop the max, so it's the same thing here, and this B is 0.0029 meters times Kelvin over wavelength in meters. And obviously, since this is a very small wavelength, it's going to be a very high temperature at which this blackbody peaks. And so let's write that down, 6.598 times 10 to the minus 16 meters. The meters cancel, you're left with units of Kelvin, and those, and the answer is 4.3 times 10 to the 12 degrees Kelvin. So over 4 trillion degrees is the temperature. Really, really hot.